think enough people have joined, so I think we can start today's session. So I hope I am audible, so someone can please say yes or give a thumbs up so that I can know from my end. Okay, so I will assume that I am audible. So with that note, so let's start today's session. So again, welcome back to the week 5 of the problem solving session for the introduction to fluid mechanics course. And in this week we will be entering to a new chapter, you can say a new chapter, a new part of this course, again quite a crucial one, that is the fluid kinematics. And just one second. And as you might have seen in the lectures, Professor Chakraborty might have discussed thoroughly about the importance of this portion of the fluid mechanics course, because the fluid kinematics part, like as we can know, is study of the motion of fluid without taking into consideration the forces that generate the motion. But again, this fluid kinematics now, like in its very self, is a very important part as it now introduces us to the governing equation of fluid mechanics. So we will, at least in the fluid kinematics part, we will deal with the continuity equation, which is basically the mass conservation equation for fluid mechanics, and we will see its functional form, like how it looks, and in terms of different flow variables. And then once we start discussing about fluid dynamics, where we consider the forces that generate the fluid flow, we will consider the momentum equation, or which is more properly known as the Navier-Stokes equation. Okay, so with that introduction, let's start today's discussion. And as per our usual agenda, I will briefly go through the concepts that were discussed by Professor Chakraborty in the lectures. I hope that you have watched the lecture, so a brief discussion on the topics will suffice for you to be able to solve the questions for this week's assignment. Moreover, after the discussion on the topics, I will briefly discuss some problems that are related to today's discussion, and the problems are quite similar to the ones that were asked in this week's assignment, so that will help you again. So I hope everything is clear, and moreover I hope I am audible. So still someone can just say yes or give a thumbs up or anything, so that I will not be just speaking to myself, to be sure. Yes, thumbs up in the chat, anything is fine. I hope voice is also, you can unmute yourself and say yes. Am I audible? Okay, then it's fine, no issues. Let us continue today's let us start with today's discussion. So here we again introduce the Lagrangian and Eulerian approach. So again, these are reintroduced. We briefly discussed about it in the first session when we started this course, and these are introduced again because now we will now work on it, like see how the governing equations of motion are obtained by understanding these different approaches. So the Lagrangian approach basically deals with the tracking of individual particles as the flow evolves, okay, or as they move through the flow domain. And the Eulerian approach is an approach where we, instead of following each and every particle, we focus our attention to a fixed point or a fixed region of flow and see how the motion of particles through that region affect the forces and the different dynamics on that particular region or fixed point known as a control volume. Okay, and again fluid particle, because time and time again we mentioned fluid particles as it is discussed here in the Lagrangian approach. So fluid particle in general does not mean a fluid molecule, but rather it is a collection of fluid molecules which on a statistical average have a common group behavior. Okay, so then we discuss about and once again just giving you a brief idea that today's session will not be that long, because this is a very theoretically heavy session. So and topics were also discussed less. So today's session will not be that quite extensive. Moreover, problems are also quite easy to understand. So it will finish really soon. So I will expect that all of you who are attending the session, please stay till the end, and let's see. It will not be that extensive like the previous sessions. Okay. So then comes the concept of steady and unsteady flow. So as per the as the name suggests, like it's quite literally understandable. Steady flow would mean that any parameter or any flow property that is independent of time, and unsteady flow would mean that the flow parameters are dependent on time. Okay, or basically as the Professor Chakraborty formally defines that at any particular point, if the fluid velocity or any property is changing with time, then we call the flow to be an unsteady flow, and if it does not change with time, then we say that the flow is steady. Okay. Then comes the concept of uniform and non-uniform flow. That again, this analysis of uniform and non-uniform flow is for a fixed time, because we need to see for how the flow property changes with space or the spatial coordinates for a fixed instant of time. Okay, so formally defining it, that fluid properties and flow velocities does not change with position or the spatial coordinates, then the flow is called a uniform flow, otherwise it's called a non-uniform flow. Again, there was a very extensive discussion. Audio not coming. Okay, so okay. Oh, okay. Extremely sorry, I was mute, so I didn't see the thanks. That's why I was again asking whether I'm audible or not. But sorry, again that's thanks Sanu for reminding it. Let me just again brief introduction for today's session. Then sorry everyone. I was mute from my end. It's my error. So I hope you understand. Sorry for the mistake. Okay. So let's again go back. So okay. Sorry for the loss of your time. Let me just briefly introduce again. So in this week's session we will be briefly discussing about the fluid kinematics. So fluid kinematics, I hope I'm audible now. Someone can say yes or no. Otherwise it's again I'll repeat the same mistake. Am I audible now? Yes. Thank you so much, Sanu. Okay. So as I was discussing, that fluid kinematics is a new chapter to this course, because here now we will be dealing with fluids in motion. Okay, up till now we were dealing with fluid in static, basically the fluid at rest, and see how different forces act in this kind of scenario. We again also discuss about fluid under rigid body motion and see how we can keep the fluid under rigid body motion under the purview of fluid statics, even if the fluid is in essence it is in motion. Okay, but once we deal with fluid kinematics, we are basically saying that we are dealing with fluids in motion, and the fluid molecules undergo shear deformation. Okay, so but here, since we are dealing with kinematics, so we will not be discussing about the forces or the driving factors that generate the flow. Rather, we will be more concerned in understanding how the fluid molecules move from one place to another, and how to analyze that motion, and how different flow parameters changes because of that motion of the fluid molecule from one part to another, one part of domain to the another. Okay. Then again, so let me reiterate again, as per the usual agenda, I will not go in detail in each and every topic. Rather, I will briefly go through the topics that were discussed by Professor Chakraborty in the lectures, and then if you have any doubt, you can stop me, of course. And then we will discuss some questions that are relevant to this week's discussion, and which will indeed help you to solve the assignment questions for this week. Okay, so everything, if it sounds fine, let me then restart again. Okay, so the fluid kinematics starts with the Lagrangian and the Eulerian approach. These are something that we have discussed at the beginning of this course. So, and I know you will know it quite well, and Professor Chakraborty has very nicely reiterated it again in this week's discussions. So Lagrangian approach basically means the tracking of individual fluid particles as they evolve or as they move in the domain. Okay, but and the Eulerian approach basically deals with the analysis of fluid motion, where we, instead of following each and every particle, rather we focus on a particular uh, uh, region of the flow field or a particular point which is known as a control volume, and see how the motion of fluid particles through that particular fixed region affects the different dynamics of that control volume, or in general the fluid parameters. Okay, we look into that. And of course the generation or the generation of the Euler approach was basically because to counteract the computational cost that was required to implement the Lagrangian approach. Okay, and I think you can understand checking each and every individual fluid particles to see the variation in the fluid properties with time is an extensive analysis. So in order to counteract that, the Eulerian approach was deduced, and it works quite well in most of the scenarios. But for the advanced, highly accurate studies, people still tend to follow the Lagrangian approach. Okay, so as we are discussing about fluid particles, then comes the concept of fluid particle. What is a fluid particle? Okay, so again this was discussed in the first week session, but again let me reiterate it. So it is basically a collection of fluid molecules which on a statistical average sense have a common group behavior. Then we look into the concept of steady and unsteady flow. So as per the name suggests, is quite self-explanatory. So any steady parameter and steady flow would mean that the flow parameter or the flow properties are independent of time. Okay, they do not vary with time. Similarly, an unsteady flow would mean that the flow parameters or flow properties vary with time. Okay, or formally defining it, at a particular point, if the fluid velocity or any property is changing with time, we call it an unsteady flow. Or else, if it does not change with time, then it is called a steady flow. Similarly, we discuss about uniform and non-uniform flows, where this analysis then is done for a fixed time, a fixed instant of time, and then we see that for a particular instant of time, does the fluid properties or the flow velocities, whether they change with position or basically the spatial coordinates. Okay, so if the fluid properties and the flow velocities do not change with position for a fixed time, then the flow is called a uniform flow, or else it is called a non-uniform flow. And again, there was a very extensive discussion by Professor Chakraborty regarding the special cases where the flow can be steady and non-uniform, and where the flow can be uniform and unsteady. Okay, so the discussion I will not reiterate, but that I think it's again a good practice to go back to that, because these kind of special cases may be asked in interviews. So to check into so that the interviewer can check your basic understanding of this concept. Okay, so now let us start the interesting part, that is the flow visualization. So as I mentioned, fluid kinematics, we will be dealing with fluid flow in motion, and fluid flow in motion is aesthetically saying it's a very pleasing thing to observe. Okay, so if you might have seen that in the case of laminar flows, if the flow is moving with a low velocity, they tend to follow tend to flow in layers, like fluid flow having a lower velocities. In simple sense I'm speaking, then say this is a flow domain. So if you put a particular dye at the inlet, and of course this experiment is again a very famous experiment by Osborne Reynolds, so on which the Reynolds number has been named. So if the flow is laminar, basically the flow is devoid of any kind of fluctuations and is ideally speaking with low speed, ideally moving with a very low velocity, then you will see that the flow tends to flow in layers rather, and you can see that the dye, like if you place different dyes, say, of different colors, say this is blue and say this is green, so you'll see that these dyes tend to flow in separate layers. Okay, they do not intermingle with each other, but rather tend to follow some straight path. Of course, depending on the flow, they can curve as well, but they do not tend to mix with each other. Okay, the laminar flow does not have the characteristic of mixing. Like they do not have any kind of mixing, and they tend to follow their own independent paths without any kind of mixing or chaotic behavior. But if the flow is turbulent, okay, let us say if the flow is turbulent, then you will see that these dyes, say the red one, the green one and the blue one, rather than initially they may follow the same path for for some period of time, and then they will see that rather than following a straight path, they will try to move in some erratic manner, irregular fashion, and so similarly this will follow initially the same path, and they will tend to intermix with each other and tend to follow a very unpredictable path. And that's again because that the turbulent in its essence have a chaotic behavior, show some chaotic behavior. Okay, that's right. So you will see that the fluid particles will tend to intermingle with each other, and they may end up in a very unpredictable endpoint. Okay, so these kind of motions fluid motions tend to show very beautiful patterns in nature. So for example, if you are looking into waves that hit the, say if you're looking under a bridge and looking into its pillar, you will see that the waves might hit the pillar or the column that supports the weight of the bridge, and you will see the interesting patterns when they hit it, when they hit them. And like if you want to visualize those physics in lab, then you can use different dyeing agents to create the same create your same physical scenario, and then try to visualize it using different dyes. Okay, and moreover, for example, the other interesting one would be something like flow past a cylinder. Okay, again that's a very famous experiment done by von Karman. So that's why for example, like again it's a flow domain. Okay, and a cylinder is placed here, and once the flow is allowed to develop past the cylinder, you will see that the incoming flow might be quite well organized, quite uniform. But once the flow goes past the cylinder beyond a certain value of Reynolds number, basically which signifies the velocity in this case, you will see that there will be generation of some interesting patterns known as vortices. Okay, this round shaped vortices you will see emerging from the trailing edge or the back part of the cylinder, and these vortices tend to have a periodic behavior and alternating behavior. So you will see that first this vortex will come, and then you will see that after some time this vortex will emerge. So they tend to show an alternating periodic behavior. Okay, so the second vortex is not from the same edge but rather from the opposite edge, and it has certain legs. Similarly, then these are alternating, and then again the period between these vortices are again periodic. Okay, or the gap between these two vortices are periodic, these two vortices and these two vortices. So it's a very popular experiment, and these vortices are indeed known as the von Karman vortices. Okay, von Karman vortices, or I must say not vortices, I can say von Karman vortex shedding. Okay, because the vortices are being shed from the trailing edge of the cylinder or the back side of the cylinder. Or in a more popular sense, another similar geometry would show similar patterns. It is the flow past an airfoil. Airfoil, like if you recall, it's the shape of the aircraft wings that we commercially use in airports or for air travel. So you'll see that similar flow domain it is considered. And now if instead of placing a cylinder, if I consider an airfoil, okay, the cross sectional area of airfoil is something like this, and I'm considering a non-uniform airfoil. So they will again tend to show similar behavior. Like vortices will emerge from the trailing edge, that is the back part, this edge, or this also popularly known as a trailing edge. So you will see that vortices will arrive from this edge, and again they will tend to show an alternating periodic behavior. Okay, even if your incoming flow is steady. Okay, steady or uniform, you see this kind of patterns will emerge. So scientists, when they look into such phenomena, they were quite intrigued that there should be some method or methodology to understand these patterns. So in order to understand it, they formed the concept of flow visualization. And flow visualization in its very essence are being primarily governed by three very popular lines, or I would say flow visualizing methods, that is the streamline, the streak line and the path line. Okay, and it's and in essence, for example, when we look into, okay, let me let me come back there once I have defined all these special lines. Okay, so streamlines, let us discuss about a streamline. Again, I'll just briefly discuss it. So again, this part I will suggest that you can go back to the lectures and revisit it again if you have any doubt, because it's a very crucial part for your understanding and should remain with you forever if you are pursuing your career that deals with fluid mechanics. Okay, so with that idea, let us go to the definition. So streamlines are the imaginary lines in fluid flow such that the tangent to these lines at any point represent the instantaneous velocity of the fluid particle. Okay, the instantaneous velocity. So these streamlines are defined instantaneously, and it's defined for a particular instant of time. Okay, again, there was a very extensive diagram and notation used by Prof. Chakraborty, so I'm just going to skip that for the sake of saving time, but I will try to discuss the governing equation. So the equation was basically derived from the fact that the tangent to the velocity and the velocity should be parallel to each other, thus the cross product of both of them should be 0. So doing the cross product and analyzing, we will find that dx by u is equal to dy by v. I'm sorry, just one second. Dy by v, and that is equal to dz by w. So that's the equation for a streamline. Okay. Similarly, when we discuss a streak line is a very interesting characteristics. That is, it is the locus of all the fluid particles which at some prior instant of time might have passed through a common point. Okay. So for example, let us consider a case where, say, this point, say x naught, y naught, is our point of injection or our point of consideration. Okay, and say we inject some dye from some dye, the dye molecules at a particular instant of time. So for example, molecule 1 might have passed through it at an instant t1. Then molecule 2, let me write it in a way so that I can draw a line. So molecule 1 and molecule 2 might have passed this point after the say at a time t2, where t2 is greater than t1. Similarly, molecule 3, sorry, I placed it numbered it wrong, so sorry for that. It should be something like, this should be the first molecule because it has covered a longer distance. This should be the molecule 2, molecule 3 and molecule 4. Let us deal with 4 molecules now. So T1, T2, T3, T4. Okay. So the molecule 1 was injected at this point and it has traversed a distance T1 plus T2 plus T3 plus T4. Okay. So after a certain time it has reached this distance, but the instant of injection of this molecule was T1. Similarly, at time T2, the molecule 2 was injected at this point. It has traversed some distance and reached this point. Okay. Then molecule T3 was injected at molecule 3 was injected at point T3, so it reached this point, and molecule 4 was injected at time T4. It has reached at this particular point. So I'm just saying, I'm considering that the flow is laminar, so they are following a straight path. Of course, the molecule 1 might reach here, then molecule 2 may be here, 3, 4 might be here. So this would be your streak line. So in this particular case, when the flow is laminar or quite steady, so you can think that this dotted line should represent your streak line. Okay, because all these points have passed through this particular common point or the point of injection and have traversed some distance, and we are finding those particles and trying to generate a locus of those particles. Okay, and the final thing of visualization or final tool of visualization is the path line. Well, it's basically the Lagrangian description of the fluid flow. What happens is that we follow, this is the locus of an identified fluid particle. Okay, so basically, like if this is the, for example, this is your point of injection, say x naught, y naught, and it was injected at some time t naught, then instead of looking into different particles, we just look into a particular molecule, say 1, which was injected at time t naught. Let us say at t1, say it has reached a distance t1, so we'll follow this particle for a certain period of time. So let us say it has followed, generated these complicated trajectories, and say after time say n, it has reached a point, reached a certain point, say x and y n at time tn. Okay, at time tn. So rather than following each and every particle, we try to find the locus of the trajectory that was followed by this particular particle that we are following from the very beginning. Okay, so this is another way of visualizing the flow field. So I hope this is clear. Let me give you one more understanding. So a governing equation for the path line is something like dy by dt dx by dt is equal to v. Okay, where x and v are vectors. So we find, say if you are doing an integration using Euler method, so say x, the instantaneous location of the particle, would be given by x naught plus v into t. Okay, so this is your final position of the particle, and this is the initial position, and this is the velocity of the particle with which it has traversed for this particular instant of time. Okay, so this is the governing equation for the path line. And again, there was a very extensive discussion by Prof. Chakraborty on how these are different from each other, how the streak lines, path lines are, and streamlines are different from their very definition. But again, there was a discussion on why we can say that for steady flows, the streamlines, streak lines, and path lines are identical. So there was very extensive discussion. I am skipping it for saving time. But this statement, for steady flows, streamlines, streak lines, and path lines, is very, very, very important. So that's why I have labeled it in red color. Why? Because from the conceptual point of view, this is a question that is asked almost every year in the engineering competitive exams such as GATE and EAC. This is asked every year. This is conceptually asked every year, and you will see in many previous year questions this question is asked time and time again. That's one thing. Second is its implementation. So all this visualization that we actually do, that is flow past the cylinder, or say tracking these paths of the particles, are actually the streak lines and not the streamlines or the path lines, because path line can be imagined, say can be understood in real sense at some it's in a some certain limitation, but by its very definition, streamlines are imaginary, so we cannot visualize them. Okay, so all these flow patterns, for example, let us focus into some specific cases such as flow past cylinder or flow past an airfoil. We are saying that, say, if these are the streamlines, or it, of course this will not be the streamline, this is vortex shading, but say if I am drawing a streamline past the airfoil, say the initial flows, showed streamlines of this pattern. Okay, so these patterns that we see because of the die are actually not the streamlines but rather the streak lines. Okay, but we are saying that these are equivalent to the streamlines. Why? Because we are assuming that the flow is steady. Okay, so for only steady flow cases, we can consider that the die that we use to visualize the flow past a particular shape or a particular flow domain, those lines are the streamlines only when we consider the flow to be steady. Okay, so that's why it's again very important from the implementation point of view. Okay, so I wanted to emphasize on it very deeply because it's very crucial for our understanding of flow visualization concepts. Okay, so I hope this is clear till now. Yes or no? Yes, thank you so much, Pradeep. So let us look into a timeline. Again, it's not a flow visualization, it's not a primary flow visualization tool, but again it's used defined in a way that helps us to understand the flow physics in a much better sense. Okay, so it's basically a snapshot of all the nearby fluid particles at a given instant of time. Okay, so that's again there was an example taken by Professor Chakraborty, the converging section where the timelines were plotted. But again, I'm just skipping it, but you can again look into it again so that you can get a better sense. Okay, so with that idea, we now come to an important aspect, that is the acceleration of fluid flow. So till now we were dealing with fluid velocities and fluid position, but now let us look into another advanced parameter, that is the acceleration of the fluid flow. Okay, so this is again very important concept to, or I would say fact to understand. That's the requirement of the Eulerian approach. Okay, so first thing, as I mentioned, it is primarily because of cost cutting, right? Mitigating the cost, that is, or the computational cost and labor is required to analyze a fluid flow problem using the Lagrangian approach. Okay, that's the first thing. But second is then why we are trying to implement it, like how we are implementing it in the mathematical perspective. So it is important because these fluid mechanics laws, the conservation of mass, moment of energy, all these were devised in a very in the from the classical mechanics point of view. These were devised for a control system, that is for a fixed mass having a fixed identity. But what we are doing here is now that we are, instead of following a control mass, we are looking into a control volume approach. That is basically the Eulerian approach. So that's why we have to change these governing equations accordingly, so that the description of our analysis fits to these governing equations, or the description that we are doing to define these fluid mechanics problems fits well with the classical laws that we are following to understand these systems. Okay, so that's why it's very important to understand the variation of the definitions, mathematical definitions of these parameters when we change from the Lagrangian to the Eulerian approach. Okay, that's why I need to be very careful while understanding it. So eventually, I hope in the next lecture or the lecture after that, we will deal with a very important theorem also known as the Reynolds transport theorem, that is basically used for the transformation from the Lagrangian to the Eulerian approach. Okay, so with that brief overview of the concept, let us discuss the acceleration part. So again, acceleration, like we usually know it as the double derivative of the displacement. So if x is the displacement, say, then velocity v is dx by dt, and acceleration a is dv by dt, or d square x by dt square. Again, this is not wrong, this is correct, and it fits quite well with the Lagrangian approach. But now we are dealing with trying to understand these accelerations from the Eulerian perspective. So we are defining the definition. We are defining the mathematical form of acceleration accordingly. Okay, so there will be certain discrepancies. So let us see. So here, from the Eulerian approach, the acceleration should inherently be the function of the space as well as time. So here we will see that since we are defining acceleration from the Eulerian perspective, these velocities are as well a function of space and time. Okay, and I will try to give you a brief example. Let us see. Okay, let us see, and so that you can understand it in a much better sense. Okay, so now let us go back to the mathematical derivation. So say if, let us consider u is a, if the u component or the x component of velocity is at a particular time is a function of x, y, z and t, the its coordinates and the time at which it is measured, then say at a defined point where the fluid flow is undergoing acceleration, so the velocity will increase. So it has increased from u plus delta u. Okay, from u to u plus delta u, and now the final position of these particles are at x plus delta x, y plus delta y, and z plus delta z, and we are measuring it at some time t plus delta t. Okay, so using Taylor series expansion, we can write u plus delta u as u plus dou u by dou t into delta t plus dou u by dou x into delta x plus dou u by dou y into delta y plus dou u by dou z into delta z. Okay, and some higher order terms that we are neglecting. And similarly for delta x, delta y, delta z, and delta t tends to 0, the acceleration ax will be given by limit delta t tends to 0, delta u by delta t would be dou u by dou t plus u dou u by dou x, plus v dou u by dou y, and w dou u by dou z. Okay, and this definition is the Lagrangian description of the acceleration. Okay, but the ones in the right hand side is the Eulerian part. Okay, and these two tend to have an equivalence when limit delta t tends to 0. So as Professor Chakraborty might have emphasized that at limit delta t tends to 0, the Eulerian and the Lagrangian description merge with each other. Okay, so you will see why, because when we are considering say this we can basically obtain this one when we take this u will cancel out, so we divide this term by delta t. Okay, so once you do that, let me go back here. So ax is equal to limit delta t tends to 0, delta u by delta t, it will become dou u by dou t. So okay, so it will be visible now. So these terms go to the denominator, and so it will be divided by all the terms, so it becomes delta x by delta t, delta y by delta t, and delta z by delta t. So this is something that we have seen here. Okay, so all these things become delta x by delta t, delta y by delta t, and delta z by delta t. Okay, and this limit delta t tends to 0, delta x by delta t, this becomes equal to u, which is the Eulerian velocity component. Okay, similarly delta y by delta t is the velocity v, and delta z by delta t is the velocity w of the Eulerian velocity description. And this becomes equal to u only when we say that delta t tends to 0. Okay, so that's why the Eulerian and the Lagrangian definition of acceleration match with each other at delta t tends to 0. Moreover, when this we are defining it is as the u velocity component, then that is the velocity of fluid particle. This would be equal to the velocity of fluid if we consider the particle to be neutrally buoyant. Okay, that is basically particles having zero density gradient. Okay, and it will just follow the fluid motion. Okay, again there was a extensive discussion about neutral buoyant particles and its significance in fluid flow visualization. So you can go back to it to understand it more clearly. So that's how this interconnection between the Lagrangian and the Eulerian velocity component and the limit delta t tends to 0 signifies that the acceleration that we are measuring from the Eulerian perspective, given that delta t tends to 0, is indeed the Lagrangian acceleration, but just defined in a sense to take into the consideration of the acceleration change because of the spatial gradients or the spatial variation of the velocities. Okay, so once you do that, then we have the different components of acceleration. So here you can see that there is one component where the acceleration is the function of time, where there is so it's not a function of only time, it's a function of time and space, but there is one component that deals with the derivative of the velocity component with respect to time only. So these derivatives with respect to time only are also known as the local acceleration. Okay, in the other terms, they deal with components that have spatial gradients, that is these terms such as dou by dou x, dou by dou y, dou by dou z. These take into account the acceleration because of the change in the value of velocity with respect to space or the spatial coordinates, and these are also known as the convective acceleration. Okay, so let us take an example. I will take one example. I hope this is it can be understood. But so let us take a nozzle. Okay, this is nozzle. Some of you, or maybe all of you, might be aware with the concept of nozzle. So it basically used to increase the velocity of the fluid flow, considering the mass conservation. Okay, so say this is V1 A1, it is the velocity at the inlet is V1, velocity at the exit is V2, and the area at the exit is A2. Okay, so from mass conservation, M1 should be equal to M2 for steady flows, of course. right? Then we will have something like rho 1 a1 v1, it is the mass flow rate at the inlet, should be equal to rho 2 a2 v2, considering the flow to be incompressible, so rho 1 should be equal to rho 2. Then we will come to something like a1 v1 is equal to a2 v2. Okay, and since a2 is less than, or let me write something like a2 by a1 is equal to v1 by v2, and since a2 is less than a1, so v2 is greater than v1. Of course, if you want to look more specifically, this is valid for subsonic flow, say subsonic nozzle. Okay, so the discussion of the supersonic part is quite beyond this introductory course to fluid mechanics, but still it's something that you should know. But let me just keep it up to here. So from mass conservation, we will have the velocity at the exit to be greater than the velocity at the inlet, considering a nozzle. Okay, so I think most of you are aware of this concept. So we will see that considering the steady flow, the increase in the velocity of the fluid particles, or say the collection of fluid particles from point 1 to point 2, is primarily because of this converging portion of the duct. Okay, because of this converging part, the fluid velocity is increasing in order to conserve the mass. Okay, so the increase in the fluid velocity is now primarily because of the change in the spatial configuration. Okay, or in other words, you can say the velocity is changing from this point to this point because of the spatial gradients. Okay, so you can consider something like, if you are considering only the u component of velocity, or considering 1D nozzle, then the acceleration of the fluid particle is primarily generated because of this part. Okay, the spatial acceleration components. Okay, and we are saying that the flow is steady, that's why we can consider mass conservation to be of this form. Okay, so since there is no temporal variation of velocity, since the flow is steady, so the acceleration attributed to this particular form is only because of the spatial gradients. Okay, so spatial gradients are basically, I am saying that this derivatives is dou u by dou x, dou u by dou y, and dou u by dou z. Okay, but you can consider some another example. Okay, where you can say that instead of having a steady case, let me have an unsteady case where the velocity at the inlet is now a function of time. Okay, let us consider a case where case 2, where velocity at the inlet is a function of time. Okay, so again, then this analysis is not valid. This will change accordingly, but you can assume something like, now I am increasing the velocity at the inlet with time. Okay, so again there will be a corresponding increase in the velocity at the outlet, but the velocity at the outlet will always be greater than the velocity at inlet. Okay, why? Because first of all, the acceleration of the velocity in case 2 is because of the change in velocity with time, that is attributed by this one, but also because of this converging portion, the velocity increases, or the acceleration occurs because of the spatial gradients. Okay, so the acceleration is now caused because of both the temporal change of velocity and the convective or the spatial change of velocity. So both of these will now attribute to the net acceleration of the fluid particles. Okay, and that's why, well, when considering these kind of systems, where our control system in this case would be the inner area of the nozzle itself, so in this sense, the velocity are the function, velocity as well as the acceleration, or all the fluid properties are function of space as well as time. Okay, so is this part clear, this example? Okay, thank you so much, Pradeep. So with that idea in mind, again, let us mathematically just show you some discussion. So let us consider this only the x component of acceleration. So ax is du by dt, which is the Lagrangian description. Then this du by dt is again considering this form of the equation, can be written something like dou by dou t plus v dot del, where v is the velocity vector and del is the Nebula operator. Okay, and I hope you are all aware with the Nebula operator. So let me just write it once. So Nebula operator is a vector operator which is given by dou by dou x I cap plus dou by dou y j cap plus dou by dou z k cap. Okay, and v is a velocity vector, so it will be something like u I cap plus u j cap plus u. So sorry. It would be v and w. Okay, so this the dot product between these two vectors. So this is again an operator. Okay, it's an operator. So ideally I should, instead of writing equal to, I should write equivalent. So something like this. Okay, similarly, so these two are the same thing, but this is the more generalized case which is valid for any kind of definition. But this is the special case where I am defining this acceleration operator or the Eulerian acceleration operator in terms of the Cartesian coordinate system. Okay, where the coordinate system is basically XYZ coordinate system. Okay, so now comes the deformation of fluid element, or basically the distinguishing factor that separates this analysis from the fluid statics. Okay, because even in the case of fluid statics, we saw that rigid body motion of fluid flow can be considered to be, or can be considered under the umbrella of fluid statics. Why? Because there was no shear deformation of the fluid element. But fluid kinematics, since it is dealing with fluid motion exclusively, so there are shear deformation of the fluid elements. Okay, and this is just the introductory part. So again, we will discuss quite extensively about the shear for the lateral strain, the shear strain, the volumetric strain, the linear strain. Everything we'll discuss. So it's just the introductory part. Okay, so deformation of the fluid element, it can be classified into two broad categories. That is, first the linear deformation and the angular deformation. Okay, and for today's session we will just be dealing with linear deformation. Okay, so the linear strain rate along the x direction is given by dou v by dou x, along the y direction is given by dou v by dou y, along the z direction is given by dou w by dou z. So this derivation was again done by Prof. Chakraborty. So for the sake of saving time, I am skipping that part, but you can go back and again just revise it to understand how this relation has been obtained. Okay, so linear strain rate basically imply the deformation of fluid element along the direction of, say, if I am considering this coordinate system, say x and y, then the deformation of fluid element along this direction will be considered to be as the the linear strain of the fluid element along the x direction. Okay, and since we are dealing with fluid molecules, so it is the linear strain rate rather than the total linear strain that is the important parameter for analysis. So we deal with linear strain rate. That's why it is denoted as Ex dot, which basically signifies the dependence with time. Okay, so it is given by dou v by dou x plus dou v by dou y and dou v by dou z. Okay, or I will not say not time, but the rate of change of the parameter. Okay, similarly, when we do further, we look into it further, the volume from the linear strain rates we can deduce the volumetric strain rate, or the rate of volumetric strain, which is given by dou v by dou x plus dou v by dou y plus dou w by dou z. So this is basically the sum of these. So it is Ex dot plus Ey dot plus, epsilon x dot plus epsilon y dot plus epsilon z dot. That would be equal to, so this can again be written as the divergence of the velocity field. So it is given by nebula dot v. Okay, this basically is the divergence of the velocity field. And the rate of volumetric strain is mathematically defined as this parameter in the left hand side. It is 1 by v times dv by dt, or the net change of the volume divided by the total initial volume. Okay, and this is equal to the divergence of the velocity field. Okay, now for an incompressible flow, it will basically mean that there is no change in the volume of the fluid element. Okay, that's what we mean by incompressible flow. So it will mean that the rate of volumetric strain is 0. So this would be equal to 0. That will basically imply nebula dot v, or the divergence of the velocity field, to be equal to 0. Okay, and this is something that you might have observed time and time again in fluid mechanics textbooks, that mention the continuity equation as this one. Okay, but if you look closely, it's actually a very special case of continuity equation that we'll eventually see how. But most of the times, if you consider say steady flow, this is the continuity equation itself. Okay, so now you're being introduced to the first conservation law that we are using to understand fluid mechanics. So again, let me give you a brief idea that for any fluid mechanics studies, or let me give you a, I will say, special understanding or special way in which you can score good marks in fluid mechanics exams. Okay, not in GATE or something like that, but say in your college exams or competitive in your university exams. Okay, so the understanding of fluid mechanics, at least the fluid dynamics and fluid kinematics part, I'll say the fluid dynamics part, all the principle that is being used to define the fluid mechanics laws are dependent on three major equations or three major conservation laws. First is the conservation of mass that correlates with the continuity equation, the conservation of momentum that correlates with the Navier-Stokes equation, and the conservation of energy. Okay, so if for any kind of problem or extensive problem, if you are not able to understand how to approach the problem, you can just start with analyzing these three conservation laws. So mostly, if we are not dealing with temperatures, then we can eliminate the energy equation. But for any kind of fluid analysis, mostly you will have to deal with the continuity and the Navier-Stokes equation. Okay, so if you start with those equations and start analyze the problem, say you define the control volume and then deduce the continuity and the momentum equation, and then try to solve for the parameters that you have to find, you can score good marks, because at least the examiner will know that you know these principles and you're implementing those principles to solve the problem. Okay, so with that idea in mind, now you are being introduced to the first conservation law, that is the conservation of mass, which correlates with the continuity equation. Okay, so let us see how it is derived. Okay, so for the conservation of mass, we have mass defined as the density times the volume, V cut, so not to be confused with velocity, so it is V cut. Okay, something like this one. Then taking log on both sides, we'll have natural log of m is equal to ln v plus ln rho plus ln v. Differentiating with respect to time, we will have something like 1 by m dm by dt is equal to 1 by rho d rho by dt plus 1 by v dv by dt. Okay, and from mass conservation, you know that mass can neither be created nor destroyed, so this is equal to 0. Then we will have 1 by rho d rho by, so not dou, d rho by dt plus divergence of velocity field, because we know that 1 by v dv by dt is equal to divergence of the velocity field from this equation. So we can substitute this with divergence of the velocity field. So we will have 1 by rho d rho by dt is equal to the divergence of the velocity plus, 0 is equal to 1 by rho d rho by dt plus the divergence of the velocity field. Okay, but again we also know that this d rho by dt can be represented in terms of this operator, which we just saw here previously, this one. So once you substitute that, you will get something like d rho by dt plus rho times nebula dot v plus rho times, oh I'm sorry, here I have done a mistake, it seems. So it should be the other way around, so it will be something like, yeah, rho times v dot nebula plus rho times divergence of the velocity field. So when you simplify this further, you can write something like d rho by dt is equal to nebula dot rho times v, where v is the velocity vector, and this is the most generalized case of the mass conservation equation or the continuity equation. Okay, see, because why it is most generalized, because it is in vector form, so we can apply any coordinate system. This is valid for any kind of coordinate system, and thus is general is the most generalized form. But say if you are dealing with a Cartesian coordinate system, then you can simplify it to this form. Okay, now let us consider some special cases of this continuity equation. For steady flow, again let me just zoom out a bit. Okay, for steady flows, this term will go away. So we'll have nebula dot rho v is equal to 0, and for incompressible flow we have that d rho by dt, or a change in the density with time, is 0, or a net change in density is 0. Basically we say the variation of density is 0. Okay, but the important thing to note is that d rho by dt does not mean that rho is equal to constant. Why? Of course rho is equal to constant will also suffice this equation, but even if rho varies, this equation will be sufficed. How? Look into this case. Let me go back here. So here in this equation, if the sum of, say if rho varies with time as well as space, then if somehow the sum of this term plus this term is equal to 0, then also this, sorry, let me okay, so say somehow if, so this is d rho by dt, right? This is d rho by dt. Okay, so if somehow d rho by dt plus this term is equal to 0, like even if rho is changing with space and time, but if this sum is equal to 0, then this condition is satisfied. So we will get something like this will be equal to 0, so the flow will be considered incompressible. But in a very simplified case, when rho is constant, then also d rho by dt will be equal to 0. So that's why rho is equal to 0 is a very special case of incompressible flow. Okay, these are very specific or niche topics that you can look into when you dive deep into the concepts, and these are the topics from where questions may be asked in the interviews. Okay, so you can look into it, but it's like, it's good to know, like if you know these things it's very good, but otherwise it's fine. Okay, so now from the continuity equation, like if you just, let me go back, if you expand this equation now, because this will basically say it's again the chain rule, so though this will be dou rho by u dou rho by dou x plus rho dou u by dou x. Okay, and similarly for all these terms, so when you expand this partial derivative, so you will be left with dou rho by dou t plus u dou rho by dou x plus v dou rho by dou a plus w dou rho by dou z plus rho dou u by dou x plus rho dou u by dou a plus rho dou w by dou z. This term is again dou rho by dou t equal to 0. So for incompressible flow, this is equal to 0. So we can write from this, we can write that this will be equal to 0. So we will be left with nebula dot v, or the divergence of the velocity field, to be equal to 0. Okay, so this form of the continuity equation is indeed the special form of the continuity equation where the flow is considered to be incompressible. Okay, so now then again we are left with the last part of today's discussion. So I will just quickly go through it. It's just again the derivation of the continuity equation in an alternate form, basically applying the mass conservation. Okay, not from the mathematical definition of mass conservation, but we look into it, say, from a control volume perspective, because this is something that we will be dealing with from now onwards. Okay, so if this is the 3D control volume, let us consider the variation of property along the x direction, and then we can accordingly add all the other changes, then find the net volumetric change. So from mass conservation along the x direction, so we will have something like m in dot m out is equal to dou by dou t, the change in the net mass in the control volume. So this is something that we discussed in the very first class. Okay, then the m dot in at x will be given by rho u into delta y into delta z. Okay, rho u, so rho times velocity times area will give you the mass flow rate. Okay, so delta y delta z gives the area, so it is rho u delta y delta z. Similarly, m in at x plus delta x, basically m out would be equal to, from Taylor series expansion, it will be m dot in at x plus dou by dou x m dot in times delta x plus some higher order terms. Okay, and this m dot in is rho dou u by rho u delta y times delta z. So from this, if we do something like, if we take this term in this in the right hand side and these terms in the left hand side, so we will be left with m dot in minus m dot out along the x direction is equal to minus dou by dou x rho u delta x delta y delta z and some higher order terms. Okay, similarly you can derive it for so we can write dou by dou t at the net change of mass in the control volume would be dou by dou t into rho times the volume, that is mass will be rho times the volume, so it will be rho into delta x delta y delta z. Okay, Now for the approximation with delta S, delta Y, delta Z equal to 0, tends to 0, we are considering a very small control volume. We will be left with something like minus dou rho u by dou x minus dou rho v by dou y minus dou rho w by dou z is equal to dou rho by dou t. If we take all these terms in the right hand side, we will be left with dou rho by dou t is equal to, dou rho by dou t plus dou rho u by dou x plus dou rho v by dou y plus dou rho w by dou z equal to 0. Or in a vector form, you can write something like dou rho by dou t plus nebula dot rho v is equal to 0, which is again the continuity equation, okay, in the vector form. So this derivation we have done or discussed for a Cartesian control volume, Cartesian coordinate system based control volume. We can do it for any kind of coordinate system according to your choice, but finally the vector form should end up in this form, which gives the mass conservation equation or the continuity equation for the fluid flow. Okay. So we will leave discussion. We'll leave our discussion up to this point, and now let us directly go to the problem solving part. So I hope the question part is visible. Thumbs up or yes would be good. Thanks, Pradeep. So let us look into the first question. Very simple problems for this week's discussion. So I believe you will be able to solve very quickly. Okay. So the fluid flow is represented by a velocity field given by v is equal to xi cap minus yj cap. The rate of volumetric strain is given by. So you need to find ex plus ey. Since it's a 2D case, so 1 by v dv by dt would be equal to this one. So you need to find this. So very simple. All the velocity components are given. A. Okay. Pradeep says A. So others, can you tell your answers as well? Very simple. Just need to do something like dou u by dou x plus dou v by dou y, because ex dot is epsilon x dot is dou u by dou x and epsilon y dot is dou v by dou y. Okay, so it's fine. So again, the correct answer is A. It's quite simple. Just take the velocity components, that is x and minus y. Take the derivative and you find something like 1 minus 1 equal to 0. So A would be the correct answer. Okay. So okay, so let's skip this question. So match the following. Again, not that complicated, quite simple. So you can tell me the correct one. Okay, look into it. Everything we have discussed, you can tell me which is the correct pair. Okay. Match the following. So irrotational flow, we might not have formally defined it. Pradeep says C. We might not have formally defined, but at least the other three we have thoroughly discussed. So even if you are able to pair the other three terms, then the fourth one will become quite simple. That the left one is the the option that is there, that should be that should match with the rotational flow. Okay, so Pradeep says C. So others, do you have any other opinions? I will give you 1 more minute. I think it's not that difficult. You can just tell me and then you can proceed. Please, others also give your answers. It will be quite nice. Saurabh says A. So I think then we can proceed. It's fine. I know all of you would be able to do it, but for the sake of saving time, and let us proceed further. So it's quite simple. Let me just share the answer. So we have just discussed, if del dot V is equal to 0, it is the incompressible form of the continuity equation. Okay. Then dv by dt equal to 0 would mean that the net acceleration of the fluid particle is 0. So r would be 4. Dou v by dou t equal to 0 would basically mean that the flow is steady, because it only depends on the derivative is with respect to only time. So there can be acceleration because of the spatial gradients, but at least from the temporal perspective there is no acceleration. So this would be equal to 0. So it is the steady flow. So the only one that we're left with is this one. So P would be 3. So P is 3, Q is 1, R is 4, and S is 2. Okay, so the correct answer should be A. Okay, is it clear? Okay, thanks Pradeep. So the next question, question number 4 is, a path line is always defined from an Eulerian frame of reference. State true or false. A or B again. True, false type statement. False. Okay, Sanu says false. Others, Pradeep says false. So yeah, I think it's quite simple now. So it is false, because we saw that the path line is itself the Lagrangian description of fluid flow analysis. So it is, path line is quite well related to the Lagrangian perspective. So it is defined in terms of the Eulerian, in terms of the Lagrangian frame of reference. Okay, so this is false. So let us look into the next question. Which of the following is or are incorrect? Okay, is or are incorrect regarding a flow field which has only convective acceleration. Okay, so convective acceleration is basically the acceleration because of the spatial gradients. Okay, it is a steady uniform flow, it is an unsteady uniform flow, it is steady non-uniform flow, it is unsteady non-uniform flow. So question is something like, okay, you can try your answers. Let me just try to simplify the question. So say we're dealing with acceleration. Say we're dealing with the acceleration as a fluid property. So it's saying that only the convective part is left. So u dou u by dou x plus v dou u by dou y plus w dou u by dou z. Okay, and dou u by dou t is equal to 0. So what can we tell about the flow field? Okay, if this is the case, then all the temporal or the local acceleration components are 0, but the spatial acceleration or the convective acceleration parts are there. Okay, so flow is accelerating because of the spatial gradients, but the local gradients are 0. So the local acceleration is, or the local or the variation of properties with time is 0. So which are the incorrect statements here? Is or are the incorrect statements? Is, oh, So is the screen visible? Okay, Saurabh, thanks Pradeep. Yes, so you can try it out. It's quite simple actually. It's just a method of elimination. So let me give you one hint. Like, let us consider the first case. So it is a steady uniform flow. Okay. So it is steady. It might be steady because dou u by dou t is 0. So the first statement is correct. But okay, Saurabh says C. So is it C is the correct one or incorrect one? We want the incorrect options. Okay, Saurabh. So you can tell whether C is the correct one or the correct one or the incorrect one. We want the incorrect ones. So correct one. Okay, thanks. So Saurabh says it's correct. So other statements are incorrect. So okay, thank you so much. So this is actually the correct answer. So options A, B and D are incorrect. Okay, how? Let us look into it. So the first statement says it is steady and uniform. So this might be steady again because dou u by dou t or the temporal variation is 0, but it says that the flow has only convective components or the convective acceleration. So the convective acceleration will only be there if the flow is non-uniform. Basically they have spatial gradients. Okay, the properties change with space. So this has to be non-zero. Okay, this has to be non-zero. So first one is not feasible, so this is incorrect. Second is unsteady uniform. Again, the first statement itself says unsteady, so this is not possible, so this is incorrect. Option D is unsteady and non-uniform. This again, the first statement again makes it incorrect. So the only correct option is C, that is steady and non-uniform. Okay. So let us look into the next question. Question number 6. Streamlines, path lines, or streak lines are virtually identical for steady flows. State true or false. I think it cannot be much simpler than this one. True, yeah. So I think I emphasized a lot of time in reiterating it again and again, so it is true. Explanation I think I don't need to give, but okay. So next question is question number 7. A fluid flow is represented by a velocity field given by Ax I cap plus C by j cap, a 2D velocity field, where A and C are constants. State the correct relationship between A and C if the flow is incompressible. Okay. So if the flow is incompressible, let me give you a hint. You can look into the form of the mass conservation equation for incompressible flow. So if you remember, for incompressible flow, the mass conservation equation reduces to this form. This is divergence of the velocity field is 0. So with that hint, can you tell what is the relationship between A and C? Saurabh says it's B. Others, can you contribute? Pradeep says it's B. One more. Okay. So yeah, it is correct. Correct answer is option B. Again, it's quite simple. The average of the velocity field would be something like dou u by dou x plus dou v by dou y would be equal to 0. This is the u component, this is the v component, so we will get something like dou by dou x of ax plus dou by dou y of cy equal to 0. This will give A, this will give C, should be equal to 0. So the correct option is option number B. Okay, thank you. So the last question is This is a bit lengthy but quite simple. Let's look into it. For a steady flow, the velocity field is given by this equation. Okay, minus x square plus 3y I cap plus 2xy j cap. The magnitude of the acceleration of the particle at 1 minus 1 is, okay, so you need to find ax and ay, okay, and find the magnitude of acceleration. So I will give you a hint. A is given by ax I cap plus ay j cap. You need to find the modulus of a at point 1 and minus 1. So this is a lengthy question, so I'll give you say 5 minutes to try to solve it, then you can let me know. Okay, so the thing is, you need to find the individual components of ax and ay, then find their value at, so replace x and y by 1 and minus 1, then replace it in this equation, then find the magnitude of a. Okay, you can take your time, 5 minutes. I will ask in 7:25. You can try, it's fine. Take your time and just try. So last 2 minutes. Again, let me reiterate, it's not a competition, it's fine. I'm just for saving time, I'm just saying, giving you a finite time, but it's fine. It's basically the concept that you need to recall properly, and the calculations. Okay, so do your partial derivatives that you're going to do with respect to x and y properly, and then substitute the value of 1 for x and minus 1 for y, and then tell me the answer. So that would be a good practice rather than trying to solve it as fast as possible. Okay, so that's not what we want, of course. But of course, speed, like if you can do it fast, it's very well and good, because this kind of simple exercises might be there in competitive exams such as GATE and ESE. So their solving questions in a lesser time matters a lot. But if the concept itself is wrong, then it doesn't matter how fast you can do. Okay, so the concept, knowing the concept is important. Doing your calculations correctly in each and every step, and then finding the answer. So that should be the chronological order of understanding a problem. Okay, but in this case, it's a very simple substitution of values and calculations, so I don't think it should be much difficult, but still. Okay, so last minute, anybody, did you get an answer? Okay, Pradeep says it's B. Okay, let us wait. Let us see the answers from others. So let me give you one more minute, say 7:26, so the others can also put in their views. Then we will look into the calculations. Okay. So it seems time is up, but please don't mind, it's just for the sake of saving the time for this session, but it's completely fine if you're like in between the your calculation is fine. Okay, so let us just look into the solution. So here we have the velocity component as the velocity vector as x minus x square plus 3y cap plus 2xy cap. Okay, so we can write ax as dou u by dou t plus u dou u by dou x plus v dou u by dou y. So this would be equal to 0 because the flow is steady. Moreover, you can see that there is no time dependence of the velocity component. So u is minus x square plus 3y, dou u by dou x would be minus 2x, v is 2xy, dou u is 3, dou u by dou y is 3. Okay, so once you do the summation, you will get something like 2x cube minus 6xy plus 6xy. So these two will cancel out, so we will left the ax component would be 2x cube. Similarly, let us look into the ay component, dou u by dou t plus u dou v by dou x plus v dou v by dou y. So usually the mistakes people do is in this writing this one. Sometimes these two gets interchanged, so that is something that you need to emphasize more. Okay, so that you are not confused in the calculations. So the one key thing to remember is that if you are calculating, let me just go back to the definition, so that you can just recall it properly. Okay, so let me, yeah, so you will see that if I am considering the ax component, then you will see that this is easy to remember, this is dou u by dou t, but the thing is it u dou u by dou v by dou y or v dou u by dou y. So the key thing to remember is that first is this factor of coefficient of u, v, w should be consistent in all the terms. Okay, that's first thing. Second one is, if you are finding the acceleration with respect to x, then the variable on which the spatial derivative operates should be the velocity component along that direction. So if you are considering ax, it should be u dou u by dou x. So dou by dou x should operate on u, the velocity component along x direction. Similarly, v dou u by dou y. So dou by dou y should operate on u. Similarly, w dou by dou z. So dou by dou z should operate on u. Similarly, for v ay, you will see this dv by dt, quite easy to remember. But the next component should be u, consistent with the first one, times dou v by dou x. So it should operate on v, the velocity component along y. Similarly, v dou v by dou y, the v, it should operate on the velocity component along y, so it is v. Then dou by dou z should operate upon v, the velocity component along y. Okay, so that's one way you can remember. And from practice, it will settle in quite well in your memory, but for beginner, like if you're just looking into it the first time, there might be some confusion that which term comes first. Okay, so I know it's quite basic, but still I have done mistakes in the past on this kind of calculation, so I'm just making you aware from the very beginning. Okay, so yeah, so it is dou v by dou t plus u dou v by dou x plus v dou v by dou y. Okay, so all the special operators should operate on the velocity component along the y direction. This is 0 because the flow is steady. U is minus x squared 3y. Dou v by dou x is 2y, right? V is 2xy, so dou v by dou x should be 2y. V is 2xy and dou v by dou y should be 2x. Okay, because v is 2xy. Then if you calculate this, you will get something like minus 2x square y plus 6y square plus 4x square y. So it will be 6y square plus 2x square y. So your acceleration will be given by 2x cube I cap plus 6y square plus 2x square y j cap. Similarly, then substitute the value of 1 and minus 1 in this expression. You will get a at 1 minus 1 as 2i cap plus 4j cap. Magnitude of a would be given by the square root of the components, the sum of the squares of the components. So it will be given by 2 square plus 4 square, that is square root of 4 plus 16 is square root of 20, or 2 root 5 units. Okay, so the correct option should be none of this. Okay, so Pradeep, did you find like where did you make the mistake? Yes. Thank you. So it happens. Okay, it's completely fine, but I just gave you an idea how to remember or understand like which operation should come after what in the definition of acceleration. But with practice, you will become quite what to say fluent in these definitions. Okay, so I hope that's all from. Thanks, buddy. That's all from my end for today's discussion. If there's any doubt, you can ask, or otherwise, let's all meet in the next week. Okay, and all the best. Gauss law. Gauss law for what? I'm not understanding. You can say it.
So for control volume, for control volume and control surface.
Yeah, Gauss divergence. Yeah, Gauss divergence theorem, right? Gauss divergence theorem, right? Changing the volume integral to the surface integral to volume integral. Okay, so I think that's actually a very basic mathematical definition. So let me just end the session of